Hey everyone, welcome back. In this video, I'm going to take a quick look at the math that we're going to need to create our Pokemon themed game. More specifically, we're going to look at vector math, linear interpolation, and Quaternions. Let's get to it. So I promise that we're going to get into coding the game pretty quickly now, but first off, I want to run you through a quick math refresher so that I don't have to explain these things when we get to it, because then we're explaining two things at the same time and it'll just get complicated. So we're going to look into vectors, linear interpolation, and Quaternions. So vectors are usually used for the positioning, the scale, the transformation of any object in your game space. Linear interpolation is used to oftentimes for animation purposes when we're moving objects around or when we're scaling objects to pretty much decide 2 points that we know and then fill out the missing information in between those 2 points through mathematics. And then Quaternions, well, Quaternions is how we're going to do rotations in a 3D scenes to avoid gimbal lock. But I'll explain all those things in a little bit more detail when we get to it. So let's start with vectors. And mathematically, vectors are typically defined by a list or an array of numbers. As you can see on the slides here, a vector will have a certain amount of dimensions that corresponds to the numbers that are part of the vector. So a two-dimensional vector will have 2 numbers associated with it, a 3-dimensional will have 3, a 4 will have 4, and a 27-dimensional vector will have 27 of them. We'll probably not use those a lot, but for this specific tutorial series, 2-dimensional and 3-dimensional vectors will pop up left and right. So the dimension of a vector, as mentioned, it describes the amount of numbers that are contained into it. Okay, so what do we do with them more specifically? Well, in geometry, a vector is used to describe a line segment, as you can see here from the image, that has both a magnitude and a direction. So the magnitude is the red line, it's the length of the vector specifically, and the direction is how the vector is oriented in the space. So in this case, phi is a vector, the magnitude is the length or the red line, and the direction is indicated by the angle that we have up here. So that's all pretty great, but what does that have to do with video games? Well, let's have a quick look at Smash Bros. Here, and we could see how we have 2 copies of NES. I'm actually going to orient myself to the CPU one because that one's on the right. And we can see that the CPU on this Cartesian axis system would be defined as 2 on the red axis, which would be a y in the 2-dimensional space, and 5 on the x-axis. So 5, 2 would be the vector in relation to the origin point that would determine the position of our CPU character in this specific scenario. So this is a way how games will keep track of where characters are on screen or where any kind of object is pretty much on screen. Now, of course, Super Smash Bros. Is a 2D game, and we can use vectors very well to describe the position of our objects in that space, but if we want to have a 3D game, we need to do something extra. And if you're thinking, well, just make a 3-dimensional vector, you're on the right track here. So as you can see on the slide here, on the left we have a 2-dimensional vector. This time it's 3 on the x and 2 on the y, while on the right we have a 3-dimensional vector that is used to describe where this specific point is in a 3-dimensional space by bringing in a z-axis or a z-axis as well. So this point would be defined by 3 on the x, 2 on the y, and 2 on the z, and then we end up right here. Now, if you're thinking like, oh, that's pretty straightforward, right? Maybe hold your horses a little bit, because 3D applications and game engines in particular, they're not really following a standard here. Every engine has its own quirks, and one of the quirks that an engine typically has is what kind of a orientation system they are using to keep track of the position of a certain object in a 3-dimensional space. Since we're focusing on Unity right now in this tutorial series, we're going to look at what Unity does, and Unity actually does it like this. It uses what they call a left-handed system, and you can actually use your own hand to make the same sign as you see on the left side, with the Z pointing away from you on your middle finger, the Y pointing upwards on your index, and the X pointing to the right on your thumb. And that is how Unity will position an object in a 3D space. So if we look at our image that we have from the previous slide as well, the z-axis and the y-axis are actually swapped in Unity. So that's important to keep in mind, because if we go back to this thing here, in Unity a 3, 2, 2 would actually mean a different point. 3 isn't on the x-axis, still going that direction. 2 on the y-axis would actually be going up, and 2 on the z-axis will actually be going to the right because we're flipping these two things. So keep that in mind as we are moving forward with Unity. You'll get used to it pretty quickly though. And with that, we now know how to keep track of a point in a 3D space using vectors. So what's up with that magnitude that I was talking about earlier in the beginning of this video? Well, the magnitude, as you can see, is the length of the vector. So it's actually very convenient to calculate the distance between any 2 points in a 3D space. Now, before we get to that, you want to know that a magnitude is usually expressed in this way in math, and we can always calculate that length if we know an x and a y value on an axis through Pythagorean theorem. However, in Unity, you're never really going to have to do that kind of calculation yourself because the vector3 class comes with a magnitude property that will do the math for you. So you never really have to worry about that part. So whenever you want to calculate the distance between 2 points in Unity, all you need is the vector that determines one of the points and the vector that determines the other point. Subtract them from each other and get the magnitude. Now, to clarify this a little bit, because we haven't looked at Unity much, transformed opposition actually refers to the game object on which the script is being run, taking the transform of that game object, so the transform contains the scale, the rotation, and the position, and then we take the position to get the vector that actually determines the position of the object. So that's pretty much what that means. So if you wanted to know the magnitude of a point between the origin and a target that you have up here, you could just take target position minus nothing because it's just the origin and get the magnitude of that. But you can also use this for 2 points that are anywhere in the 3D space, and we'll look at that in a little bit. Okay, so with that, we now know how we can get the distance between two vectors. How can we scale vectors up and down, as I was discussing earlier? Well, we can do that by a simple multiplication. We multiply the vector with a scalar, which is basically just a number. And the result of doing that will be a vector that's parallel to the original vector, but with a different length. Let's look at the example here. So say we have vector v that is at 2, 3. If we multiply that by 2, we get vector 4, 6. Pretty straightforward math. If we multiply it with a negative scalar, we're pointing in the opposite direction. So minus v will become minus 2, minus 3, because we're multiplying with minus 1. And please note that this arrow is pointing to the left and down, while the other ones are pointing right and up. So that's pretty much how we can make an object bigger, smaller, by multiplying the vector that determines its scale with a number. So that is multiplying vectors with scalars. What happens when we do addition and subtraction with a vector? Like I was talking about it earlier, we can calculate the distance between any 2 points in a 3D space with addition and subtraction. How does it actually work? Well, to add 2 vectors, all you have to do is add the corresponding components of the vector, and that can be very helpful for movement and relocation. So as you can see in the example here, if we have this vector up here, which looks like it is 2 on the x and 3 on the y, if we add to that a vector which is 2 on the x and 0 on the y, we basically get the combined result here, which will be 4 on the x and 3 on the y. So that makes sense because we are doing 2 plus 2 and 3 plus 0. So 4 on the x and 3 on the y, as you can see illustrated here. Similarly, looking at the other illustration, if we are subtracting the b vector from a, we get 0, 3, because again, this time we are subtracting 2 from 2, and we're subtracting 0 from 3. So that is how you can add and subtract vectors from each other. And as you can see, these can be very useful to figure out the distance between 2 objects in a 3D space, or to move one object from one vector to the next. Okay, so let's do a little test here and see if you get this. How would you go about calculating the distance between 2 players? Just give it a pause if you have to think about this. All right, so moving on to the answer, and let's bring out Smash Bros for this. So if you want to figure out what the distance is between CPU-ness and between the player-ness that we are seeing here, what we basically would want is we want the distance from this vector to that vector. So that is pretty much a new vector that we want the magnitude of. So all we have to do to figure out the distance between both of them is do the subtraction and get the magnitude of it then, which basically, if we do the subtraction, we are taking this vector here, moving it down here, then it would come down to basically the magnitude from this vector. So to illustrate that a little bit, we are subtracting the -3 minus or 2 vector down here to get the vector down here. And if we take the magnitude of that, we know the length that would be between both of these characters. So that is pretty much how you can find the distance between two objects on screen, which is what we already discussed earlier in this video. So let's have a quick look at what that looks like in raw math. So if we take player position 1, we have x1, y1, z1. And if we do player position 2, we have x2, y2, and z2. So the distance between both of them would be the magnitude of position 1 minus position 2, or with Pythagorean theorem, we basically get to this. However, if we want to do this in Unity, we don't have to worry about anything of this. We could just take position 1 minus position 2 and get the magnitude of that. Easy peasy. Now, as you might have noticed with that little exercise, it is very convenient to work from the origin point to perform certain operations on your vectors. And one of these operations that we will use from time to time is called normalization. So normalization is a unit vector. It's a vector that has a magnitude of 1. So pretty much what you would get is if you draw a circle with the origin point of your Cartesian system in the middle, you would have a unit vector as the radius of that circle, and the vectors that are pointing from the origin to the boundaries of that circle are unit vectors. Now, as we will see, these kind of vectors are going to be useful for a lot of different things. The only thing you want to know at this point is if you want to have a vector that is normalized in that kind of a way, typically it is to figure out what kind of direction a vector has. All you need to do is grab the vector and divide it by its magnitude. And that will give you a vector that fits within that unit circle with a radius of 1. Which brings us to direction, as I was already indicating, because the direction of a vector is usually represented using these unit vectors. So as you can see here, it's a lot easier to look at a vector as 0.8, 0.6 rather than 4.3 to figure out what the direction of this vector was kind of going to be. So Unity has two ways that you can use to normalize your vector to go from here to there. You can use vector.normalized, which doesn't modify your original vector 3, or you can use the vector normalized method that will modify the vector that you output here. So two ways to do this, and depending on the scenario, we'll demonstrate which one is the preferred one. Unity also has a shorthand for unit vectors. They have vector up, down, forward, left, right, all sorts of names for it that writer will happily help you remember, and it will pretty much output the unit vectors in this format. So for instance, vector up will become 0, 1, 0, because the up would be 0 on the x, 0 on the z, and just 1 on the y. And with that, we are getting towards the end of my little refresher on vectors, but I do have to say, the trickiest bits of working with vectors are going to be at the end, because we're not nearly done yet at all. So up until this point, we've discussed how we add vectors for distance between points and how we subtract them for a similar purpose. We talked about scaling and multiplying vectors with a scalar, which can be a floating point number or an integer. And we've talked about dividing vectors to get a normalized unit vector version that we can use for direction. And that's all great. But what happens when we try to multiply vectors with each other? What does that even mean to multiply one vector with another? Well, there's two ways that vectors can be multiplied. And the first way is through a dot product. So let's have a look at that right now. So the dot product of two vectors is expressed by vector 1 with an actual thick dot in between it and vector b. And it is really the sum of the products of corresponding components that results in a single scalar value. So the way you multiply a vector, it would be somewhat similar to adding them. You just grab the x1 and x2, multiply those, and then add y1, y2, and then you add z1 times c2. And you don't actually ever have to calculate this yourself again, because Unity's vector 3 class has a method to calculate this called dot. So you can just use that, and you never really have to worry about the math and making any mistakes while you're writing your code. You can just put it in the dot method from the vector 3 class. So what is this thing actually good for, if anything? Well, I'm glad you asked. If you remember that unit circle, it actually has some pretty cool properties. X and Y right now on this slide are used to denote the two axes, with X going left and right and Y going up and down. Now, if you look at this vector A and B, the A value denotes where we are on the x-axis, and the B value denotes where we are on the y-axis. Pretty straightforward. But if you look at this through the lens of some Pythagorean theorem, you might remember from your high school math that x is actually the same as the cosine of this angle here, while y is equal to the sine of this angle here, and b over y is the tangent of this angle. So not to go too far in that math, but the dot product mentioned earlier would then be the same as the adjacent over hypotenuse, which is the same as the cosine of this angle. So if we invert that, we can calculate any intercepted angle of the unit circle, so basically the angle between 2 points and the origin of a circle, by taking the arc cosine of the dot product, which is described down here. And that is absolutely wonderful, because now we can calculate the angle between any 2 points in our 3D space pretty easily, just by normalizing the vectors and using the dot product. And even better, Unity will make this thing easy again, because there's actually a function, or rather a method to the vector3 class, that will do all this math for you. It's called angle. So this is really great, because we can use this to figure out what this angle is, and even more so, just knowing what the dot product is will already give us a ton of information. You see, this is what you can read just from the dot product. So if a dot product is exactly 1, the unit vectors will be pointing in the same direction. So at this point, if we get a dot product that is exactly 1, we know that the object that we are calculating the dot product from with our origin point is exactly straight in front of us. That can be super useful for so many game applications. Similarly, if the unit vectors are pointing in opposite directions, so if something is straight behind us, it's going to have a dot product of -1. So you can see that in the visuals here, and it doesn't have to be up or down or forward, like, it can just be left, but in this case, A and B vectors are pointing to the right, so we're going to get a dot product of 1, because the cosine of them is going to be 1. Similarly, with a cosine of 180, if they're pointing in opposite directions, we're going to get -1. So that's something that we can figure out with our dot product. And if we end up with a 0, we know that we have a 90-degree angle and we're perpendicular to one another. So that is information that we can just immediately get from looking at the dot product. And I'll explain at a later point how you can apply this for some very cool uses in a video game. For now, however, I'm going to ask you a question. How would you calculate, knowing all this, if something is in view of the player? Pause the video if you need to think about it. Okay, well, here's actually a clip that I got from the internet, made by NetMakesGames, that really illustrates this well. And as you can see here, this is what the dot product becomes between these two objects. And it is actually being used here to figure out if this object in a 2D space, but you can also use it for 3D space, is visible within this radius or not. And the calculation here using that angle method is actually pretty straightforward, and we'll end up using it in our game as well. So if the dot product is close to 1, we'll have it in view, and you can just then be like, okay, let's have an angle of maybe 25 degrees or something. So if we're in between 0.75, we know that we're kind of in view of our player. So that's a way that you can easily use a dot product to figure out if something is going to be in view or if something is not going to be in view. And that's one way to multiply two vectors. However, there is another way that you can multiply two vectors and get another equally cool outcome. And that is by calculating a cross product. So a cross product of two 3D vectors A and B will yield a 3D vector, so not a scalar anymore, that is actually perpendicular to the plane created by both A and B. So this can be really useful as well if you need to know what that up direction would be. So the calculation for a dot product is a little bit tricky. As you can see here, it turns into this thing, but we'll get to that in a bit. Let me first show you a visualization of what this perpendicular actually means and how that actually looks like. So again, I got an animation from someone who put something together that is way better than what I would have possibly been able to provide you with. And this one comes from Dragonite Spam. So notice that the resulting vector that you're seeing here, the blue point, it's not rotating, it's not spinning, it's simply moving up and down as the y, or well, in Unity this would be the z and this would be the y. The blue one would be the y in Unity. But yeah, you can see how it moves around and how the resulting dot product vector is going to be going further away from the origin and closer to the origin. Now, one reason why I'm bringing up this visualization is that I want you to notice that this is not meaning that everything is perpendicular. The green axis and the red axis can be absolutely not anywhere close to 90 degrees. They can actually be fairly close to one another. And you will still have a good read on the direction for the y-axis or the z-axis, depending on what kind of coordinate system that you're using. So keep in mind the cross product vector will be perpendicular to the other two vectors, but the other two vectors do not have to be perpendicular to one another whatsoever. Okay, now getting back to how we calculate this very useful cross product, it is noticeable that it's not as easy as just multiplying the x's, adding the y's, multiplying the z's. No, it's all over the place, really. As you can see here, the x value that we want is equal to y1 times c2 minus c1 times y2. So you probably want to have something that will help you memorize that. And to do that, we use XYZ. So if you look at this, x is equal to y1 times z2 minus z1 times y2. And you can deduce the other ones by just going down the alphabet then. So after the y's become z's, the z's become x's, and vice versa. So that's how you can memorize this thing, as long as you keep in mind that you have to subtract and that you go 1, 2, 1, 2. Now, of course, do we really like to memorize stuff? Not really. So we can just use Unity's Vector3 class, and they have a cross method to just calculate this thing as well whenever we need it for our games. All right, great. That solves everything we needed to discuss about vectors. Let's move on to linear interpolation. So linear interpolation is basically a way of calculating the value of a variable between 2 points that we already know. So say we have a vector A and a character is there, and we have a vector B that we want our character to move to. We can calculate where that character needs to be when the character is 30% along the way, 50%, 60, 70, 80, and we can make our animation go along that path by doing linear interpolation. The formula for that is you have your A vector and your B vector for the origin and the target, and T is an interpolant typically clamped to the range of 0 and 1, where we want to calculate the vector where our character is going to be when we are in that specific part of the range. So at 0, our character will be at the origin, and at 1, our character will have reached the destination. So to put that in another example, if you have an object moving from position 1 to position 2, the halfway position would be this formula using these vectors multiplied by the interpolant of 0.5. Now, you don't really have to worry about this again because Unity has your back. The Vector3 class has a method called lerp. It even has a method for spherical interpolations, and you provide it with the starting point vector, the target vector, and then the interpolant t, and you can figure out where your character is going to be at any given point in time, if that is what the interpolant t is going to end up signifying. It does that a lot. So anyways, that's linear interpolation. We'll see it in practice as we start working on the game. And that means that we can get to the last one, and we are going to have to take another look at rotations because we're going to have to discuss quaternions. So let's have a quick recap and look at how we can express angles in Unity. So first, there are the axes. There's an x-axis, a y-axis, and a z-axis, as we've already described. Well, we can also talk about pitch, yaw, and roll. As you can see from the example of a plane for which these terms are usually used, we have a certain pitch. We have the pitch would actually be the x-axis in this case. We have a roll, which would be the z-axis in Unity. Remember your left hand. And we would have a yaw, which would be the y-axis in Unity for rotating along that way. So yaw, pitch, and roll is a common way to illustrate how an object is rotated in a 3D space. And oftentimes the pitch, yaw, and roll of any object in a 3D space will be described using Euler rotations, which is very common in math class as well. And I'm sure you've worked with these before. And if you look at Unity's inspector, because Eulers are something that we can all really easily wrap our brain around, Unity will use them to rotate an object in a space. In the transform rotation, these values for x, y, and z are all expressed in Euler rotations. So that's pretty great. But even though it's really easy for us to grasp them, they come with a pretty big downside. Let me show you. So this is an animation made by Gorilla CG, and it actually shows you the principle of gimbal lock. So you can see how we have our 3 axes and how we can use them to rotate this plane in a 3D space. However, at this point, 2 axes align, which means that we lose 1 axis. We can no longer rotate the object in 3 different axes because 2 of them are going to lead to the same result. So if you want to move that plane's yaw at this point, there's no axis that actually allows you to do that. We can still do the roll, we can still do the pitch, we can just not do the yaw anymore. To get the yaw, we would need to do a pitch and a roll first, which is a big problem if for, I don't know, a 3D animation, we would need a yaw to be our next step. So that is the principle of gimbal lock. And to fix that, Unity uses something else than Euler rotations. It uses Quaternions. Now, before we go there, notice how Euler's 3 rings can influence each other as well. Rotating the outer ones, and I'll show the animation again, rotating the outer ones actually also rotates the inner ones. And in Unity, the order in which that will happen will be the z-axis, the x-axis, and then the y-axis at the very last. And if you start animating objects in Unity, that's going to be relevant because objects will be influenced in multiple ways by rotating those outer axes. Okay, so how does Unity then use Quaternions to solve this gimbal lock issue? And while we're at it, what are these Quaternions even? Well, Quaternions are a double cover rotational system. As Euler rotations are using a vector of 3 dimensions, Quaternions are using a vector of 4 dimensions, so that there is never a single component of your vector that is covering a full rotation. With Quaternions, 2 components will be in charge of any single rotation, and it depends on what you're trying to do, which components that are going to be. Needless to say, mathematically this can get a little bit complex, and visualizing this is not nearly as easy as visualizing Euler rotations. So to solve that issue, to solve the difficulty that comes with the visualization, there is actually a really good website designed by Ben Eder on Quaternions that I'm going to forward you to because it will explain Quaternions in a way that is so much better than what I could possibly do. It will let you interactively mess with Quaternions and see what the results are of what you do with the math and what you do with the numbers that you're inputting. It's absolutely amazing, and I strongly recommend that you check it out. For the purpose of this class though, since Unity is going to take care of a lot of the things that we're going to be doing, this is what I want you to keep in mind. When we're using Euler, the pros are that they're easy to understand and they have very simple representation. And a lot of engines will use this as a default way for you to input an angle. However, it can be really difficult to figure out how to combine rotations because you'll end up with that gimbal lock issue. It can be very difficult to figure out if 2 rotations are the same because rotating over 0 or rotating over 360 is pretty much the same thing in some kind of way. And it can be pretty hard to interpolate between 2 rotations when you're passing the 360 threshold. So Euler has a lot of issues, and Quaternions fix most of those issues, and they are mathematically absolutely fascinating. The only issue that you have with Quaternions is that they have 4 components, 3 of which are a vector and 1 is a scalar component, which makes it pretty complicated to understand and to manipulate. However, when it comes to Unity, we will never ever have to adjust them individually, and I am telling you right now, don't ever try to adjust them individually because Unity always has a method that can do it for you. For instance, if you want to know what the rotation of a certain transform in your world space is going to be, so the transform is the position, the scale, and the rotation of an object, You can just use GameObject.transform.rotation, and that will output the quaternion and you can manipulate it. You can also use quaternion.angleAxis, in which you provide an angle and an axis, to just have a rotation happen, which all the math will happen through quaternions, but you don't have to worry about it. Sometimes, though, you want to put in an angle through regular Euler degrees, and you can use two math functions, rad to deg and deg to rad, to make the conversions between radians and degrees whenever you need to as well. Finally, keep in mind, if you're using quaternion angle axis, that your axis needs to be a unit vector. So if you're using it, make sure you normalize it, for which you can use the functions that we discussed earlier in this video. Oh, you're still here. Okay. I wasn't expecting anybody to make it this far. Thank you so much for watching my entire math video. I hope it was very educational and informative. I know that sometimes it got a little bit abstract, but I promise we're gonna make this Pokemon themed game. It's gonna be super fun, and all these things that I talked about are gonna be applied. And in the meanwhile, I'll make sure that in the additional readings for this class, you'll get some sites and some YouTube videos as well, where people have made some really great visualizations or applications of the things that I've talked about in this video as well, that you can review if you want to get a deeper understanding of these things. And with that out of the way, we're really going to start cranking up the dial on making the Pokemon themed game. So I'm looking forward to seeing you in the next video. Again, thanks so much for sticking around to the end. I'll see you in the next one. Bye-bye.